Jai Hind Jai Hind everyone. This is Naresh Kumar from Ajay Kumar Garg Engineering College. Welcome to another class of optical communication. So this is video lecture on the scattering losses. So basically in this lecture mainly we will deal with the or study with the attenuation or loss mechanism occurring inside the optical fiber cable. That is, in this lecture we will study that what happens when light propagates through the optical fiber cable and what are various mechanisms which are responsible for signal attenuation as well as losses or reduction in the strength of the signal. So the main contents for this lecture will be attenuation or losses in the fiber. Then we will cover the absorption type of losses occurring inside the optical fiber cable. Then we will cover the scattering losses, and finally we will discuss the fiber bending losses. So first of all we will discuss the attenuation. So what is attenuation? Basically in the optical fiber, whenever the light is entering the fiber, the power is more, but whenever the optical signal is exiting from the optical fiber cable, there is reduction in the strength of the signal and there is reduction of power, which results into the attenuation. So basically during the propagation of signal into the optical fiber cable, there is reduction of power. This reduction of power or strength in the signal is termed as attenuation. So attenuation, like gain, is measured in terms of decibel units. So in the optical fiber communication, there will be one power known as input power and second will be output power. Due to attenuation, the output power is always less as compared to the input power. This difference of power appears as the attenuation or losses inside the optical fiber cable. Here the attenuation term is used as a general term. Basically we are not considering any type of mechanism, that is which type or what mechanism is responsible for reduction in the strength of the signal or power of the signal, but there is reduction in the strength of the signal in general because of any loss mechanism. So attenuation here is used as a general term for the loss occurring inside the optical fiber. That is, all type of losses occurring inside the optical fiber cable are combinedly termed as attenuation, which can be calculated as number of decibel or losses 10 log pi by p output. So as discussed, there can be a number of mechanisms which are responsible for attenuation that we will discuss in the further lecture in detail. These mechanisms attenuation mechanisms can be, for example, absorption loss, maybe scattering loss, or maybe because of bending of the fiber, that is bending loss, and sometimes we also use the connectors and splices for connection of two fibers or components with the fiber. So those also result into the losses or attenuation. So the attenuation or losses occurring inside the fiber are total losses, which can be represented as total loss, and we know that these total losses may be represented as a function of length of the fiber. That is, as the length of the fiber increases, losses inside the fiber will also increase. So these total losses may be divided per unit length of the fiber, that is denoted by the alpha. So here we will use the term alpha, that is attenuation coefficient, which denote the loss or attenuation per unit length of the fiber. That is, in 1 kilometer length of the fiber, how much loss or attenuation is occurring. So the total losses may be combinedly represented as a product of alpha into L, where this alpha is loss coefficient. So next is types of mechanisms or type of losses occurring inside the optical fiber cable. So first type of loss or mechanism inside the optical fiber cable is absorption loss. Absorption losses are also known as the material absorption losses, because here the strength of the optical signal gets reduced because of the absorption of the light by the material of the fiber. We know that optical fiber is made up of glass or plastic. So whenever light will interact with this glass or plastic, some amount of light will be absorbed by the material of the fiber. So this type of losses appear as the absorption loss or material absorption loss. Now the types of these absorption losses can be, there are two types. One is intrinsic absorption, second we will cover that is extrinsic absorption. So we will study the difference. What is intrinsic absorption? So basically intrinsic absorption is a loss mechanism in which the strength of the optical signals get reduced, but this absorption mainly occurs because of the basic material structure of the fiber, that is pure glass material of the fiber. Let's say optical fiber is made up of silica glass. So the amount of light absorbed by the silica glass material, that is pure glass material, is known as the intrinsic absorption. As we know that the basic material will be required for making the fiber, so minimum amount of intrinsic losses will always occur. Even if the fiber material is pure, we can't do anything about that. So intrinsic absorption is mainly because of basic pure fiber material, and let's say silica is the glass. So because of silica, the losses are absorption losses, and these occurs near the operating spectral band, that is 0.8 to 1.7 micrometer wavelength, and these absorption losses appear as the windows or in the region form, that is a particular region of intrinsic absorption will be there, a particular region of extrinsic absorption will also be there. So now we can see that there will be effect of absorption of light over the fiber material. Whenever the fiber is in contact with the light, some amount of light will always be absorbed. So we have to take care that proper suitable material is selected for making both core as well as cladding. That is, by the proper selection of material, by using pure fiber material, only then we can reduce the intrinsic absorption losses. So here is the diagram for the attenuation losses occurring as an intrinsic loss mechanism in the pure glass material. So here we can see that this is the total loss occurring inside the optical fiber cable, and the intrinsic absorption loss appear as ultraviolet absorption as well as infrared absorption. So mainly the intrinsic absorption will appear in the ultraviolet region and in the near the infrared region. Now the second type is extrinsic absorption. This is also second type of the absorption loss mechanism occurring inside the optical fiber cable. The extrinsic absorption is differ from the intrinsic absorption by the fact that intrinsic absorption mainly occurs because of the pure glass fiber material. Here the impurities are not considered, that is, but in the case of extrinsic absorption, the absorption losses occur because of the impurities present in the fiber material, or we can say that the impurities present in the fiber material will result into absorption of light, that is known as the extrinsic absorption. So extrinsic absorption mainly occurs when there are impurities in the fiber material, when the also the fiber fabrication process is not pure, when the fiber fabrication process is impure, okay, or we can also say that there are impurities present in the optical fiber material. These impurities maybe can be, for example, transition metal impurities, okay, there can be transition metal impurities which result into the absorption of light. Another reason for this extrinsic absorption can be the absorption of light by the hydroxyl OH ion or the water content present in the fiber. So whenever the water content or hydroxyl ion OH negative will be present in the optical fiber material, then also there is absorption of light. So absorption of light may be caused by the impurities present in the fiber. These impurities may be the transition metal impurities, or these impurities may be in the form of hydroxyl ion or water content. And this will also result whenever the fiber fabrication process is not pure. So instead of conventional melting technique, we have to use the pure fiber fabrication process such as vapor phase oxidation. That is, for reducing the extrinsic absorption, we can use the VPO technique, that is vapor phase oxidation, which is pure as compared to conventional melting techniques. So in this way we can reduce the extrinsic absorption. So here is one example of impurities present in the optical fiber material that cause the extrinsic absorption. So we have studied that transition metal impurities can cause the absorption of light present in the fiber material. So transition metal impurities can be these, like chromium, carbon, copper, iron, nickel, manganese, vanadium, etc. So here is one example. Let's say, for example, if we are operating at this wavelength 725 nanometer, and if one part of impurities is present into 10 raised to power 9 part of fiber, then absorption loss of 2.7 dB will be caused. Okay, 2.7 dB per kilometer will be caused, which is a significant amount. So here we can see that various examples, like iron content is present in the fiber material at this wavelength, then 0.68 dB per kilometer extrinsic absorption will be caused. So this is the diagram showing the effect of hydroxyl presence or water content present in the fiber material. So we have studied that if hydroxyl ion OH negative or water content is present in the fiber material, then there will be absorption of light by the fiber material because of presence of this water content. So that will cause the extrinsic absorption here. So in this, when the water content is present, we get basically the overtones here. First overtone, second overtone and third overtone. Basically at these particular wavelengths, whenever the water content is present in the material of the fiber, absorption will be rapid absorption and a large amount of loss will occur that result into the fundamental stretching vibrations. These fundamental stretching vibrations are known as the overtones. So the extrinsic absorption will result the overtones at specified wavelengths whenever there is absorption of water content or OH negative ion content present in the fiber material. Next loss mechanism occurring inside the optical fiber cable is scattering losses. So scattering losses is as clear from the name, whenever inside the optical fiber cable there is waveguide perturbation. Example of waveguide perturbation can be, for example, irregularity or cut at the core cladding interface, axis of the fiber is not straight, diameter of the optical fiber is not uniform, impurities are present in the fiber material. So there can be any reason. So whenever there will be waveguide perturbation inside the fiber, these waveguide perturbation will result into the scattering of light. So the presence of waveguide perturbations inside the optical fiber cable result into the scattering of light, which cause the scattering loss. The main reason we can also say that the mode coupling or mode mixing is the reason or cause for this scattering losses, or which may be due to the presence of the waveguide perturbations. Now, what are the types of scattering losses? So, scattering losses mainly are of two types, linear scattering and non-linear scattering. So, we will study that there are two types of scattering. Scattering losses can be of maybe linear, and scattering losses can also be non-linear scattering. So, first of all, we have to study what is the difference between these two scattering, that is linear and non-linear scattering. So, first of all, here we will discuss only the linear type of scattering losses. So, scattering losses are of two types, linear and non-linear. So, we have to first of all differentiate linear scattering from the non-linear scattering. There are some characteristics through which we can identify whether the scattering is linear or non-linear. So, the characteristics may be, for example, in the linear scattering, the power is transferred due to mode coupling or mode mixing from one mode to another mode. The power is transferred from one mode to the adjacent mode in a proportionate manner. And another characteristics of linear scattering is that power is transferred from one mode to another mode without any change in the frequency. That is, before scattering of the signal and after scattering signal, there will be no change in the frequency of the signal. And another characteristics of linear scattering can be that the linear scattering mainly occurs at comparatively low optical power levels, and there is no requirement of threshold power or voltage for the linear scattering. Okay. So, the linear scattering, we can say that there are three main characteristics for the linear scattering. One is power is transferred in a proportionate manner. Second is there will be no change in the frequency of the signal after scattering. And third requirement is it occurs at low optical power levels, or we can say that linear scattering is not a threshold scattering. So, based upon these three characteristics, we will say that the scattering losses occurring are linear scattering. Now, linear scattering can be further of two types, Rayleigh scattering and Mie scattering. That is based upon the size of the inhomogeneities or irregularities. So far we have studied that the main reason for the scattering losses is waveguide perturbation. So, one example of waveguide perturbation can be irregularity or cut at the core cladding interface. So, this is cut at the core cladding interface. So, this irregularity or cut at the core cladding interface can also be responsible for the scattering losses. So, now the size or dimension of this irregularity or cut, size of this irregularity or cut at the core cladding interface will be compared with the operating wavelength lambda. So, we will compare the size of the inhomogeneity with the operating wavelength lambda. So, in the case of Rayleigh scattering, the dimension of this irregularity is inhomogeneity is random in nature, and it will be comparatively small as compared to the operating wavelength. So, we can say that whenever the irregularities are random in nature and size of the inhomogeneity is very small or small as compared to the operating wavelength, the resulting scattering loss is known as the Rayleigh scattering, and vice versa for the case of Mie scattering. In the case of Mie scattering, the size or dimension of this irregularity or cut at the core cladding interface will be larger or comparable with the operating wavelength. So, here we can see that in the case of Mie scattering, the dimensions of the irregularity are large. So, chances of more scattering are also more. So, we can say that the Mie scattering is significant or dominating as compared to the Rayleigh scattering. Now, we can discuss this Rayleigh scattering in further detail. Okay. So, Rayleigh scattering as we have already covered, the Rayleigh scattering mainly is a type of linear scattering, and the main reason is that the Rayleigh scattering intrinsic loss mechanism which occurs between the ultraviolet and infrared absorption region. In the previous diagram we have seen that we have used the total losses in between and scattering losses in between, and there were two windows, infrared absorption and ultraviolet absorption. So linear scattering occurs generally between these two regions. Another is, we know that the Rayleigh scattering mainly occurs because of inhomogeneities or irregularity. Now, if the size and nature of this irregularity is random in nature and it is on small scale as compared to the operating wavelength, that is size of inhomogeneity, size of irregularity is compared with the operating wavelength lambda. If this irregularity is small as compared to the operating wavelength or occur on a small scale, then the Rayleigh scattering will occur. Okay, so it can be mainly reduced or improved by the index fluctuation and inhomogeneities, removing the inhomogeneities. So we can improve the Rayleigh scattering just by reducing the size of inhomogeneities and irregularities. Now the Rayleigh scattering can be represented or computed using the Rayleigh scattering coefficient. Here this gamma is the Rayleigh scattering coefficient. So the Rayleigh scattering can be measured using this Rayleigh scattering coefficient gamma r, that depends upon mainly this refractive index, photoelastic coefficient, isothermal compressibility coefficient, Boltzmann constant and fictive temperature. So there are the conditions related to temperature, optical fiber and compressibility, photoelasticity etc. of the material that will decide the amount of Rayleigh scattering occurring inside the optical fiber cable. So from this Rayleigh coefficient we can calculate the transmission loss coefficient or transmissivity of the optical fiber. Okay, so this gamma will be computed here and this gamma will be used in this formula for computing the transmissivity or transmission loss factor inside the optical fiber cable. We can see that again the losses or attenuation is occurring as a function of length of the fiber. That is, as the length of the fiber increases, always losses will increase. Next is Mie scattering. Again this is also a part of linear scattering or type of linear scattering, and the difference was that the size of inhomogeneities, if the inhomogeneities are greater in size or are comparable with the wavelength lambda, then the Mie scattering will occur. Okay, and in the case of Mie scattering, the size of inhomogeneities is large, or we can say that this Mie scattering will be significant in amount as compared to the Rayleigh scattering. So how these inhomogeneities can be reduced? So as we have studied, the main reason for the linear scattering or scattering losses is waveguide perturbations. So if we have to overcome the linear scattering losses, we have to reduce the size of these inhomogeneities present in the fiber. So these inhomogeneities can be improved by removing imperfections due to the glass manufacturing process. So when the glass is manufactured, we have to use the pure fiber fabrication process, that is impurities must be as low as possible. For example, instead of conventional technique, we can use the vapor phase oxidation technique, which is comparatively pure. Okay, then we can use carefully controlled extrusion and coating of the fiber. Okay, so to protect the fiber, we have to use the coating over the fiber. So whenever the coating is to be extruded over the fiber, it must be done carefully so that the pressure over the fiber is, lateral pressure over the fiber is uniform, and the inhomogeneities or irregularities are as low as possible, and diameter throughout the fiber is same. Another can be by increasing the fiber guidance in the fiber, which can be simply improved by increasing the relative refractive index difference delta, which is a design parameter. So by controlling this value of delta, that is relative refractive index difference, we can also increase the guidance within the fiber. So by using these three methods, we can reduce the inhomogeneities present in the fiber. Next is nonlinear scattering. So we have already studied that the scattering losses occurring inside the fiber are mainly of two types: linear and nonlinear. Linear and nonlinear. So we have already discussed the three characteristics of linear scattering. Now what are the main characteristics for the nonlinear scattering? As we have discussed, in the case of scattering effect, there will be mode coupling or mode mixing, that is power of one mode is transferred from one mode to adjacent mode, or may be transferred from backward direction to forward direction within the same mode. So that is, in the case of scattering process, there is transfer of power. So now for the nonlinear scattering, there are some characteristics. These characteristics are, that is, power is transferred in a disproportionate manner. Power is transferred in a disproportionate manner. In the scattering type of losses, power may be transferred from one mode to adjacent mode, or maybe in a single mode from one direction to another direction, that is in the forward direction, backward direction, or maybe in the both direction. Now, if the power is transferred in a disproportionate manner, we will say that this scattering type of loss is nonlinear scattering. Another characteristics for the nonlinear scattering loss is change in frequency. Another characteristics of nonlinear scattering is change in frequency, that is before scattering and after scattering. The signal before scattering will have different frequency, and signal after scattering, after nonlinear scattering, will result into the change in the frequency of the signal. Another characteristics for the nonlinear scattering is that this mainly occurs at higher optical power levels. At higher power levels. Okay, so the three characteristics can be summarized as power is transferred in a disproportionate manner, there will be change in the frequency of the signal after scattering, and third will be that it generally occurs at higher optical power levels as compared to linear scattering, or there is certain amount of threshold power, and if that threshold power is crossed, only then the nonlinear effect will occur. Now next is further types of scattering loss, nonlinear scattering. Nonlinear scattering can be further of two types: stimulated Brillouin scattering, that is also known as sometimes SBS, and another type is stimulated Raman scattering, that is known as SRS. Okay, so nonlinear scattering is of two types: stimulated Brillouin scattering SBS and stimulated Raman scattering SRS. So first of all, we will discuss the stimulated Brillouin scattering, also known as SBS. So there are certain characteristics which are common to both that we have already discussed, but in this case, as we have already studied, in the case of nonlinear scattering, there will be change in frequency. change in frequency, and we know that here the carrier signal is light, so the change in frequency of the light, that will be similar, or maybe we can say that that is basically a kind of frequency modulation. So nonlinear scattering will result into the frequency modulation. So we can say that here the scattered light will appear as upper and lower sidebands, which are separated from the incident light by the modulation frequency, or we can say that the scattered light appears as a kind of frequency modulation. Another is that in the case of scattering, after scattering, along with a scattered photon, we get a scattered photon plus a phonon, another particle, a phonon is also generated. But in this case, in the case of SBS, the additional particle generated, which is known as phonon, here a phonon will be of acoustic frequency. Okay, so in the case of SBS, what we get is a scattered photon and a phonon, and this phonon is generally of acoustic frequency. Next is, we have already studied that the power is transferred, that is mode coupling or mode mixing will occur from one mode to another adjacent mode, or maybe from one direction to another direction. So where the power is transferred in the case of this SBS, so the frequency maximum shift is in the backward direction. Okay, so SBS is mainly a backward process. So in the case of stimulated Brillouin scattering, power is transferred in the backward direction within the same mode, or we can say that the SBS is generally a backward process, backward direction process. As we have already discussed, there is certain amount of power threshold, that is non-linear losses or non-linear scattering will occur only when the optical signal power is above some threshold value. So the threshold value for the case of stimulated Brillouin scattering, threshold power is given by this formula. Okay, so the threshold power for the case of SBS is given by this formula. We can see that it mainly depends upon the parameter D, that is fiber core diameter. Then we have lambda, which is the operating wavelength. Then we have alpha dB, that is fiber attenuation or loss coefficient. And then finally we have V, that is known as the spectral line width of the source or bandwidth, source bandwidth, which is generally measured in the gigahertz. So by controlling these parameters, we can also control this threshold power required for the nonlinear scattering losses. Another type of nonlinear scattering losses is stimulated Raman scattering. Stimulated Raman scattering, also known as SRS here. Okay, like the SBS process, this is also a nonlinear scattering process, and there are common characteristics we have already studied, like the power is transferred in a disproportionate manner, there will be change in the frequency after scattering, and it generally occurs at higher optical power levels. So there is, so threshold is also required. And as compared to SBS, what is the difference with the SRS? The threshold power required for SRS is more than SBS. That is, SRS occurs at comparatively higher optical power levels as compared to SBS. And again, like the previous case, in the case of SRS, in the case of SBS, what we have is, we have a scattered photon, we have obtained as a scattered photon plus a phonon. In the previous slide we have studied that after scattering a scattered photon is obtained and a phonon is obtained. But the main difference between SRS and SBS is that in the case of SBS, the phonon was of acoustic frequency, but in this case a high frequency rather than acoustic phonon, in this case a high frequency optical phonon is obtained. Optical phonon which has a high frequency. So the main difference between the two is that in the case of SBS we have obtained is acoustic phonon, whereas in the case of SRS we are obtaining a high frequency optical phonon along with the scattered photon. Now the threshold power, optical power level required for SRS is given by this formula. So again the threshold power depends upon the diameter or size of the optical fiber, operating wavelength lambda, and attenuation or loss coefficient alpha. So the main three parameters are diameter, operating wavelength lambda, and loss coefficient alpha that decide the threshold power level required for the nonlinear Raman scattering.